Welcome to the Bytecode, where we look at smart contracts with the people who wrote them. I'm your host Shafu, and today's episode is with Philogy. Philogy, thanks for taking the time, man.
Yeah, of course. Thanks for having me on. Honor to be here and present some code today.
Awesome. So Philogy is gonna present his METH implementation, which is wrapped ETH in huff. So, Philogy, why don't you briefly introduce yourself, introduce your project, and then let's jump into the code.
Yeah, hi everyone. For those who don't know me, I'm Philogy. I like to write technical content about smart contracts, and where I focus on gas optimization and security. Currently, I'm working on a startup focused on improving DeFi security with circuit breaker standards and surrounding infrastructure. So, particularly, what is METH and why did I create it? METH is a reimplementation of wrapped Ether, specifically the very popular WETH9 smart contract. So very often in DeFi, you might want to handle ETH, which is like the native gas token, and like normal ERC20s. And then to make your contract simpler and to provide like an abstraction, you basically wrap native ETH in an ERC20 token, wrapped Ether, to provide you this abstraction so you can only handle one type of token, which is ERC20s. So the reason I rewrote this very popular contract in METH is because turns out this contract is extremely popular. And based on some stats that I found, it consumes about 5 to 10% of all gas on Ethereum yearly. So rewriting it in huff in a highly optimized manner, already seeing improvements of like 2 to 4% on just like basic calls, and then you'll see 10 plus percent improvements on like more general calls, will lead to like pretty huge savings for like DeFi protocols and users. So that's why I'm writing this.
Awesome. Sounds really cool. Yeah. Why don't you start sharing your screen? And yeah, this is, by the way, the first episode about huff. So very very exciting to have you on here. All previous episodes were Solidity. So huff today, maybe Viper next time, and then we have all three major languages, I think, which is pretty cool.
All right, can you see my screen?
Yeah, maybe if you zoom in a little bit more, would be helpful. That
Like
sounds good. Seems good. Yeah.
All right. So let's start. First of all, let's notice that this file is a bit large. There's a lot of like repeating code, but in generally, if you're not familiar with huff, it's basically you're basically writing EVM bytecode, which is basically instructions one by one. Which is very verbose. It takes up a lot of lines, like the same thing you would do in Solidity. And one line is like 10 to 20 to 30 lines in huff. What this allows you to have like full control over everything and create really optimized contracts, because often these high-level compilers like Solidity, Viper, or even the Yule compiler are not that great at optimizing certain types of things. And if you just think about them manually, it takes you much longer, but allows you to have much finer control. So for those of you who are not familiar with huff, I'm going to give you a really quick crash course, although this does assume you're familiar with bytecodes. So the first concept is macros. So the starting macro is like main, but basically macros just take whatever their body is, basically like the instructions, and it just inlines them. So for example, I'm calling here this macro that I've defined called fn dispatcher core, or function dispatcher core, and basically whatever code is there, when it gets compiled, it's going to get put one-to-one. So you can imagine it like a function call, but it's not entirely the same, but it's basically like a function call. Then you might see these labels, so it's basically like a name and colon. So this is like a jump destination. So in Solidity, you might have if branches or loops, but the EVM only has jumps. So you say jump to a certain location, it's like go to in other languages, or conditional go to, which allows you to do branchings and ifs. And then these labels are basically an easy way for you to handle these jumps, because if you imagine that this jump is at a certain position in the bytecode, if I add some operation here, like let's say I add 1 byte here, this is a multiplication operation, will get compiled to 1 byte, then it'll change the position of this label. So basically this just allows the compiler to set the positions for you and let you to think about the actual logic instead of where everything is positioned precisely. So now that we got like the super basics covered, let's get into it. So first of all, the first interesting piece of METH is the function dispatcher. So I wrote a small blog post about this if you want more details, but basically what function dispatchers generally do is they take the selector from the call data and then they tell you where they jump to a position in your code where the function is actually placed. So starting here, I have this function that gets a selector for me, and then I actually need to determine which function to go to after I have the selector. So usually how this is done in Solidity or Viper is that the code will just like compare selectors one by one by one by one until it finds a selector that matches and then execute that code. I do it a bit differently, doing some bit magic. So basically, the first instruction here is I duplicate the selector because I'll need the selector again later. So I have it here duplicated to the top of the stack. And then I do 2 bit magic operations. So the first one is the selector is 4 bytes, right? Which means 32 bits. So the first thing is I put this shift value, which is 18, and then I shift right, which means that I basically take the top 14 bits of the selector and I push them down and I basically erase the lower 18 bits. And then the next thing I do is that the lower 6 bits, I think it was, if we go to the top, yeah, the lower 6 bits, I then mask them. So basically what this leaves is you have 32 bytes minus 18 is your 14 left, and then you keep, but you basically cancel out or you delete, you clear 6 bits. So you have 8 unique bits, or basically 1 unique byte. Because what I noticed with METH is that all functions, they have a selector, right? But all the selectors, their first byte is unique. So basically use that to directly convert it with these 2 bit magic operations to a jump destination, and then I just directly jump to it. And then this jump will jump down here to one of these locations. So if you see this dest underscore thing, that's like the first byte, right? So if the first byte is 0, 0, it'll jump here. If it's 0, 1, it'll jump here. All the way down, you have all of them till the last byte is 0 FF, but you don't even need 0 FF because here it's the revert. So if you wonder what all these no matches are in between, every single no match is that it's just a selector that doesn't exist. So all the selectors that start with DF, METH doesn't have them, so this no match macro that gets inserted here, if you look at it, it just reverts. So it pushes to zeros with the return data size, and then it reverts. So that's the function dispatcher. So far so good, or we can dive into a function already, if that makes sense so far. Also, one thing you'll notice as well is that each of these functions. So for example, here the name selector, which is this, starts with 0x6, so it starts here. It has a bunch of padding because each of these function blocks, basically in the dispatcher, are intended to be 64 bytes long. So this allows me to save some gas later in terms of branching instructions because so first you jump based on the first byte, but then you want to actually check that the selector matches, because imagine somebody calls my contract with a different selector, right? Let's say they call with 0x06, but then it's like DD13, some random other thing, which is not the selector of name. Well, ideally you still want it to revert because they might be expecting to call something else, and if you still execute some function, it might cause a bug on their end. So to protect them, I still compare the selector, but this is done together with other checks to save gas in certain functions. So we can go into that in a second. Any questions so far?
So instead of using Solidity, when you compile Solidity and you have this, basically you compare 4 bytes to get the correct function. You only use you only use 1 byte, but once you jump, you actually compare all 4 to make 100% sure that you're at the correct destination.
Exactly. So I just use the first byte to jump there, and this means that regardless of what function I call, it's always going to use the same amount of gas. And then when I'm at the actual position in the code, I can actually check if the selector matches. So this just ensures that regardless of what function you call, the initial gas to get to the function will always be the exact same. Versus Solidity, depending on how it orders the functions, it might use more or less gas depending on the order of the functions that is laid out by the compiler. And usually overall, it'll also use more gas. So this way, it just saves gas and is also consistent gas between all functions. So now let's get into like a simple function, or like a simpler function. So let's look at deposit. So deposit is an exception here, because deposit actually is based on a fallback function. So basically, if you send no call data, you just send ETH, it's going to wrap it for you. So instead of checking the selector, it'll actually check that the call data size is empty. So if you look at this receive check, what it does is that it looks at call data size, and if call data size is non-zero, the jump E instruction will actually jump to the empty revert label, which is defined here as simply reverting. So this, this checks that you're actually calling the valid function, because when you load from call data, like when you get the selector over here, it uses a call data load. But if you have no call data, right, empty, so you're calling a fallback, it'll just give you 0. So we can just treat it as if it was the 0 byte. And then if we go down here to our magic, it'll land at the 0 location. And then we can check that it's actually empty call data, because at this point we don't know if it's empty call data yet. We don't know if it's like actually the fallback function, or if somebody called, maybe, somebody called with selector 00 or 128, something like that. So this checks for that. And then we have the actual logic for deposit. So first of all, there's this parameter return data size. That's just what I use to push 0. So since the recent Shanghai hard fork, there's an actual push 0 opcode. But the reason I don't use it in this code is because I want this contract to be backwards compatible on chains that don't have that opcode yet. So I use return data size because return data size only costs 2 gas. But if you don't have a call yet, it pushes 0 to the stack. So if you look at the deposit function over here, or let's do macro deposit. Yep. And then we have the macro here. You see it's defined as the variable z0, which is the push 0 opcode. So let's go to the actual deposit macro. So if you see the deposit macro here actually calls underscore deposit, and then it stops, right? So it executes whatever logic you have in underscore deposit, and then it ends the control flow. So if we look at here, it's actually a super simple function. So basically, first thing is we push the caller to the stack. This is like message sender and Solidity, except here it's just like one instruction. So you push that to the stack, and then I directly do sload. So in Solidity or something, the way you have a mapping. So in Solidity, if you had like a mapping, like mapping of address to uint called balance of, what this would actually do under the hood to calculate the slot, for the storage slot, is it would basically do the catch-hack hash of, I think it was this order. So it would do your address and then concatenate that with the actual slot in the storage layout. So in this case, it might be, I don't know, like 1 or 2. And then that would be your slot. But here, to save gas, instead of, I could do the same to keep up with Solidity's conventions, because we don't have any other mappings, is I just take the address directly as the storage key. So I don't do any hashing in between, and this saves also some gas because I don't have to put things in memory, compute the hash. I just directly push it to the stack and then load. And now I have the balance of the caller, of the message sender. So these two lines are the same as balance of message sender, you can imagine. And then I push the call value. So this is the opcode for getting message value and Solidity. And then I just add the two. So I don't do any overflow checks, because this saves gas again, because here I assume that the total amount of ETH in circulation will never overflow 1 uint 256. So I don't have to do an overflow check. Like assuming everything else works in the contract and you have a valid balance, this addition should never be able to overflow. So now that I have the updated balance, which is marked by the tick here, I push the caller again. And then now I do store. So this basically stores the updated balance. So these lines altogether are equivalent to balance of message sender plus equal to message value, essentially, in an unchecked block. But this is done with just 7 instructions. Actually just with 6 instructions, because this is already for the event. And that's updating the balance. So now we go to, now we push the caller to the stack again, because we need it for the event. So now we emit an event. So events in Solidity are kind of magic in the sense that they do a lot under the hood. So an event in Solidity here would just be like emit deposit, message sender, message value, and you'd be done. But the way it works under the hood is you have this opcode called log2. And the log2 takes the 2 index arguments, which means the signature of the deposit event and also the actual address that deposited, but also the bytes for the amount. Because here, if you imagine the Solidity code, it looks like you just have 2 parameters, right? But under the hood, you actually have 3. You have the actual byte encoded data of the event, and then you have the indexed event, the index field, which is the sender, and you have the index field, which is the signature of deposit. So what I do here is I push the call value to the stack. And by the way, these comments, it's like not part of the language, but it's like a convention. So this macro, if you look at before where we called it in our deposit function, is caller was on the stack before we called deposit, before we called emit deposit. And then here I specify that 1, it takes 1 argument from the stack. And then I also put the comment here to indicate, okay, what does it take from the stack? It takes a 2 address. So this Z0, if you're not familiar with huff, as we mentioned at the beginning, this is actually return data size, just to push 0 on the stack. And this is still 0 at this point because we didn't do any external calls, so it's still 0. And then, so we have call value and 0, and then we store it in memory. So if you imagine memory now, from byte 0x00 to 0x20, not including, you now have message value stored in there with this mstore. Because because the log opcode to emit events actually reads from memory. So now event hash is also a helper from huff. It basically computes a push 32 opcode that'll push the signature of the deposit event, which is defined in our interface over here, down here. So it'll compute the hash of this and it'll put it on the stack at compile time. So the hash won't actually get computed in your runtime bytecode. And then what I do to save gas actually here, so this is something that you couldn't directly do in Solidity without inline assembly, is instead of 32, I push 16 to the stack. And then I duplicate it and then I log. So what this says is that, okay, I have these two indexed events, which is the signature of deposit and the to address. Because remember, this code is essentially emit, deposit, message sender, message value. But now I'm also telling it that from the 16th byte in memory onwards, I am logging only 16 bytes. So usually if you would do this in Solidity, it would ABI encode the amount, which would be 32 bytes. But logs are kind of expensive. Every single byte in the extra data of a log costs 8 gas. And in practice, if you think about it, the total supply of ETH, we said before the total supply of ETH should never exceed like UN 256, but also in practice, I think, especially in Ethereum, but also even on other EVM chains, you can reasonably expect that the total supply of ETH will never exceed 2 to the 128 way. So this means that this message value, this call value, should never be larger than 16 bytes. So instead of pushing a full 32 bytes into the log, I only push 16, and this saves 128 gas because the other 16 bytes in the log that Solidity would put there would always be 0. In practice, it would always be empty, so basically wasted space. And here, I save some gas by not putting those. And that's the full deposit function. So after this is run by deposit, in underscore deposit, it just stops. And that's the whole deposit function. So that's one single function in huff.
Yeah, I think that makes sense. Obviously, I opened up evm.codes on another monitor just to, so I had to check for the log opcode, for example. I think that's useful to have to go through. Maybe you can open up to show what I mean. Like there is. If you're not super familiar with all the opcodes, there is evm.codes, which is a super helpful resource.
Absolutely, yeah. I use evm.codes all the time when I'm writing huff because unlike what it might look like, I don't actually know all the opcodes by heart all the time. So I actually have to look at the opcodes. So for example, log 2, it takes the topic 1, topic 2 from the stack, but also the offset and size in memory. And if you look at the gas cost here, so if we imagine our memory size is 32 because we wrote to it already, and then we put 32 bytes, as Solidity would put, that would cost us 13,081. But if we only put 16, that is only 1253. So that saves us 128 gas, as mentioned before. So that's why I did that. And that's the advantage of huff, really, is that you can take advantage of these really low-level things and cut a lot of corners that Solidity wouldn't allow you to cut, or like remove also a lot of clutter and extra opcodes that Solidity would add that you just don't have to add. The downside is, of course, that code looks like this, right? So what you would do in Solidity with one line is like 8 lines. Oh no, sorry. This function, like to emit a log, is like 7 lines of like semi-cryptic instructions versus Solidity. It would be very clear and human readable. But that's what I try to do with these stack comments everywhere. Is I try to make at least the variables that are on the stack more clear, because Huff doesn't have variables. It doesn't have a way to track different things or to give you like nice human abstractions on that. You have to like keep a track all yourself. So comments are key in terms of saying, okay, right now the stack I have call value, I have 2. In the next step I have 0, call value 2. And then next step I only have 2 because mstore used call value and 0. So this kind of thing just lets you keep track of it in a more human way.
Yeah, the stack comments are super helpful. It's probably a bit annoying when you write the code to keep the comments updated, but that's just how it is.
I think in VS Code there are some tools that actually do that automatically for you, like they generate some stack comments for you. But I currently am using NeoVim, so I don't have necessarily access to all the same tools that VS Code does, but I have a lot of the same things. Also, another thing you might have noticed looking at Huff code is that all numbers are in hexadecimal, because as far as I know, Huff currently doesn't support like decimal numbers, only hexadecimal numbers, so they all have to be written this way. So 16 is written as 10 instead of 16. In hexadecimal, this would actually be 22. So that's another thing to watch out for. So that's also what the comments can help with, is like, okay, hexadecimal, not that intuitive. What does it mean? So it helps here as well. So now let's look at another function. Let's look at a slightly bigger one now. Let's look at the withdraw from function, because it's doing quite a few things. So the withdraw from function, it starts up here. So it starts up here, and this is a very interesting case actually in METH as a whole, because this label, so the selector of withdraw from is 9.4 blah blah blah, and the next label is actually not free. It's not a no match. It's actually a function. So, and the withdraw from function is much larger than the 64-byte block that each of these destination represents. So basically what I had to do is I had to split up the function in such a way that exactly where it ends is actually the branching instruction that jumps like all the way down to the end after there's more space. So if you look at all the way down here, is actually where the function ends. So these 2 bits, only this macro is the actual end of the withdraw from function that is called at the top. And the reason this is done is because the function that is right after, where were we? 0x94, the function that is right after is the symbol function, and we want it to be valid, right? We don't want to mess up our function dispatcher, so this needs to be like valid code over here, so we need it to end over here. And actually the tight is so fit is that this doesn't even have any padding right here. But let's dive into it. So first of all, this is again different, right? So versus the deposit function, which just check call data size, we're actually checking the selector here. So Huff, when you write func sig, what it actually does is it pushes to the stack the withdraw from selector, right? So I don't comment it here because the pattern is the same for all functions. But then here, I have a valid non-payable check. So this function over here, it checks that 1, the selector matches, and 2, that the call value is 0. So if you look at it, so jumping, the initial function dispatcher jumps to here. So actually the actual selector is already on the stack, and then funcsig pushes withdraw from to the withdraw from selector to the stack, and then this macro actually checks. So first it checks that they're equal, right? It compares the 2 values and pushes whether they're equal or not to the stack, and then I push message value to the stack. And then I check that message value is 0 and that they're equal. So the way I do this is with this not A and B macro, but this not A and B macro is actually just a less than opcode. So how does this work? How do I use, wait, where were we? Okay, so how does it work? So let's swap it out. Because less than, so the reason this works, because you could imagine that the naive way to do this would be, if you're writing UL, is you would do AND, right? You want these 2 conditions to both be true, and then you do is 0 for your message value, right? Which would be call value in assembly, and then also your condition that it's equal selector and the actual sig, right? That's how you do it. But this one extra operation costs 3 gas, right? So there would be 3 gas for the is 0 and another 3 gas for the AND, which would be 6. All right, and less than is only one operation, which in this case only costs 3 gas. So it's a 3 gas saving. And the reason this works, and also what I put in the not A and B macro, is less than. If you imagine that the one value is a 0 or a 1, right? So you want this value to be 0 and this value to be a 1. If this value is 0, you cannot have anything that's less than 0, right? In integer terms. 0 is the lowest number because negative numbers are not compared by less than. You have the signed less than opcode, but I'm using the normal integer less than. So that means it'll always be false, right? So if it's 0, we have our condition of that it's always false. Now if it's 1, so our first condition that we want is true, then the other condition can only be true if its quote-unquote value is less than 1. And the only way it can be less than 1 is if it's 0. That's the only possible value that'll satisfy this. So that's how this thing works, and that's also something you learn doing huff, is that there's a lot of like opcodes or a lot of things that you can shorten just by using different combinations of opcodes. So also commented here, instead of doing and is 0 A and B, you can just do less than A and B, and that's why I also wrap it in a macro, although it's just one opcode, is because it may not always be intuitive why less than works this way. So I put it in a macro that's called not A and B, and then for the auditors or the reviewers who are checking this, they can see, okay, that's actually what it does. So that's how I compare both the selector and the message value in one, and then I'm not actually branching it, right? I just create a value that is 0 if anything is invalid, and that is 1 if it's all valid. So going back to my withdraw from function, so now that's the first argument it takes. It takes no error, is at the bottom of the stack. And then it starts adding a bunch of stuff. So now it pushes 0 3 times on the stack, so now it's no error, and then 0, 0, 0. And what you'll notice in this part of the code, actually because of the zoom in, the stack comments are a bit messed up. I'll zoom out if that's okay. Can you still see the screen well?
Yeah, it's okay.
Because the stack comments are a bit... Because I have wrap. Maybe I can set no wrap, and then I can zoom in. Okay. I can zoom in again, and now it won't wrap the stack comment. So you won't see the full stack comment because it's off to the screen. But basically, back to the code, you'll notice that these zeros that I push on the stack, I don't use them for a long time. I don't use them here, I don't use them here. If you go to the next macro that I call, I don't use them here, I don't use them here. I don't use them all the way until we're over here, right? This is the final point where I use them. So why would I push them all the way at the beginning? Why would I push them all the way at the beginning? Well, because of this amount value. You see this amount value that I load at the very beginning of my withdraw from function, withdraw from start, that I load at the very beginning from call data, right? It's call data load of 0x24, I get the amount. Because this costs 6 gas. Loading the amount costs 6 gas, but duplicating it on the stack. So if you look at this place here, I'm not sure if I'm duplicating the amount. Yeah, like here I'm duplicating the amount, dup 5. This costs 3 gas, but getting the amount fresh, like directly from call data, costs 6 gas. It's 3 gas more. So if I didn't put the zeros here later, and I kept amount on the stack, what I'd have to do is, if you imagine the alternative code, so that let's say some alternative universe where the actual stack is not, I didn't prepare all these zeros in advance because I didn't need them yet, I just had amount and column. But I need all these zeros to be before. So I need all these zeros to be before because of the send ETH macro, which is actually just calling call, right? And I call to send ETH, I call, and with no data. So let's go back here. So the zeros need to be under amount and caller in the stack, right? So this is lower in the stack and this is higher in the stack. So this would mean that I would need a swap instruction. And a swap instruction costs 3 gas, right? So to save on that, I basically put the zeros in advance at the correct spot. And even though they're not used for a long time, all the way at the end of the function, it saves me that swap instruction for the send ETH. So that's the kind of things you can do with huff by just managing a stack that Solidity wouldn't necessarily do, because it doesn't have like that foresight of seeing, okay, you will need this stack value very down the line, so let's save one swap instruction by basically reorganizing your entire code to push these values earlier. But yeah, going back to the initial code, so
that's really cool.
Oh, yeah,
that's really cool, Philogy. That's really interesting. Okay. No, continue. Just.
Yes, that's why I love Huff, because there's a bunch of like these small things you can do that really allow you like to push the gas further. But yeah, continuing the code. So the first part, as the comment says, is we're just setting up the stack and loading some parameters. So we're getting amount from call data, we're getting the address. So here I have a little macro, but basically all it does is it cleans the address, because according to the ABI standard, which is how function calls need to be formatted for different contracts to understand them, is that an address, which is actually only 20 bytes, is 0 padded to be a full 32 bytes. So in Huff, if you load it directly from call data like this, like a load amount, it could have so-called dirty bytes. So in the padding of 12 bytes, what if somebody doesn't put padding, right? It could be an address, but with extra bytes, right? So to make sure it's cleaned, I have this load address macro, which basically loads from a different position, call data, and then shifts right to make sure that the top bytes are always empty. And the reason this is important is because one, I use the address directly to load the balance. And also I use it, I hash it for the allowance slot to read the allowance. So what this would mean if the bytes were dirty is that somebody could manipulate like what value you're reading for the balance and for the allowance, and could be a potential security vulnerability. So it does cost a little bit more gas to clean the address instead of just loading it directly. But sometimes you need to do that for safety reasons. So yeah, I load the address using this macro. And if you're interested in what this macro looks like, it's very simple actually. It loads call data, so it gets 32 bytes, and then it shifts down by 96 or 12 bytes to make sure that the top is cleaned, and then it shifts right to actually do the shift. So that's how it works. Oh, whoops. Where were we? Yeah, we'll draw from the start. All right. So now we have the allowance macro. We have these values on the stack, and we have this macro get allowance that gets called. And what it does is it does two things. Actually, technically three things. So first of all, it determines the allowance slot, because unlike balance, allowance is a mapping from an address to an address. So if you would do it in Solidity, it would be mapping address to another mapping of address to amount. To uint, and then it would be a public allowance thing. So it's like, if you imagine where in storage it is, you have two keys. You don't have a single value key, you have two keys. So to do this in a safe way, similar to Solidity, but not entirely the same, I hash the from, so the owner and the spender to get their slot, or like the allowance. So to do this, I have the from address, and then I put that in memory, and then I have to put the caller in memory, which in this case is the spender, and then I compute the hash together. So all these opcodes just place the different values in memory, because the hashing opcode only hashes data which is already in memory, right? Because the SHA-3 opcode, which is the Huff name for the catch-check opcode, takes the start of memory and the size, right? So 0, start at 0, and hash 64 bytes, and then pushes the hash to the stack. So that's how I get the allowance slot. And then I load the allowance slot to get the actual allowance onto the stack, right? And now I check if it's infinite. So this is like a common optimization you'll see in ERC20 tokens, even in OpenZeppelin or Solidity, is that they'll check whether the allowance is a certain size. Like if it's really large, like if it's a max uint, you don't actually need to waste gas to update the allowance, because it'll never get depleted in practice anyway. So what you do is you just skip the update. So that's what I do here. That's this inf allow dest parameter. It's basically the location or where I should jump to if the allowance is infinite. If it's infinite, like skip the update and then it runs different code. So if you go back to where get allowance is called, here in withdraw from start, we have the code that runs.
Philogy, this is super interesting. I didn't know that. I didn't know about that optimization. So, okay, if it's above a certain number, they just don't update the allowance?
Yeah, exactly. We can actually check it out very quickly in a common implementation. I think OpenZeppelin at this point also does it. Let's check it out over here. Oh. All right, there we go. So if we look at the transfer from function, transfer from, yes, spend allowance, it should be in here. Spend allowance, exactly. So it first retrieves the current allowance, And only if the allowance is not the maximum, only then will it actually update. So this just saves gas because doing an allowance update or like doing a storage update costs 2,900 gas from a non-zero to a different non-zero value if it's already warm, which would be this case. Or if we did like some arithmetic expression, we could change it to an S store from the same value to the same value, but that'll still be 100 gas. So this branch in the function is definitely worth it because a branch is actually quite expensive gas-wise. It's like 13 gas plus 1 for the branch where you're actually landing because there's a jump test which costs 1 gas. It is kind of expensive, but if you think about the S store that you save, which costs at least 100 gas, up to 2,900 gas, it's definitely worth it. So going back to our withdraw from start, we have all this code to actually update the allowance, but we skip that if we don't have, if the allowance is infinite. So if we skip that, we have this label, and then we jump all the way straight to here. So we skip all that code. Now note, this macro also has the withdraw from balance check. So this actually checks the balance. If we go up here, it compares the balance to the actual amount and then reverts if it's non-zero. So we skipped that balance check as well. So we want to still check the balance, right? Even if the allowance is infinite, we want to make sure we're not creating tokens out of thin air. So we still have the balance check here. But if you remember, huff actually inserts all macros in place. So when this gets compiled, the entire code of withdraw from balance check will be placed here, but also here. So we're basically duplicating code in our final bytecode, making it larger. So why do we do this? Why do I not just put a label here? Like let's say, let's call it withdraw from continue. And then what I could do, technically is I could pop the value here because when we land here at withdraw from, we still have some values from the allowance function we don't need. So in this situation, it's cheaper to pop them off the stack using pop, and then we continue with this stack. But we're duplicating code here, right? So what if I just jumped over here instead of duplicating all this code? I could just do withdraw from continue jump. Well, this jump, even though it's non-conditional, is quite expensive. It's 3 gas to push the label onto the stack, which is basically after compilation the location in code where this is, and then the actual jump, which is 8 gas. And the jump test, which is another gas. So that's actually 12 gas total. So instead of doing that, because I don't care about the code size, right? Because the code size is only a cost when you deploy. When you deploy, you pay for every byte you deploy 200 gas. So even if I'm adding like 300 bytes over here, I'm paying at deployment 300 times 200. I'm paying 60,000 gas more, right? So that's probably a few dollars. But that's worth it here, right? Because the whole goal of METH is to save gas for users and end applications. And they will be executing this jump every single time for the rest of time, right? Until the contract is not used anymore. So saving the 12 gas over here in return for making the code slightly larger is definitely worth it, in my opinion, because that's the whole goal of METH. So then we calculate. So yeah, then we have this macro, which actually checks the balance. So we could look at the detail of like how the allowance gets updated, but basically it's a swap to get the allowance. So it's swap for the error, and then we just check if the allowance is smaller than the amount, and if so, we flip like this error that we had at the beginning. If you recall, that's the value that tracks whether the selector and message value were valid, and then we pass that on, and then we update the actual allowance, and then we pass it on to the next function, which actually checks the balance. And then the interesting part here is that if you notice, for the selector, for the message value, and even for the allowance down here, I didn't use a branching instruction once. So if you imagine what it would look like in Solidity, you would have a require, but every single require is a branch, right? It would check that the condition matches, and if it doesn't, but it checks the condition by having a branch there, right? By having a conditional branch that says, if it's a certain value, jump to revert. If it's not a certain value, continue. But as mentioned a lot of times here, they're quite expensive. So instead of doing it a bunch of different times, like you imagine a require for every single condition, I accumulate all these conditions into one no error value. So this no error value, if any of the conditions before were invalid, this no error value will be 0. And then what happens here, at the very end, I also do the balance check. So whether the amount is larger than the balance, I all put it into one no error value. And then at the very end, what I do is, if the no error value is 0, then it won't jump, and then it'll just revert over here. But if it's non-zero, that means all the previous conditions were true, we can just continue our code, and we can jump to the complete withdraw from code. So this reduces, you could have, in theory, up to 4 different branches, once for the selector, once for the message value, once for the allowance, once for the balance, are all combined into one single branch over here, which then actually finishes the code. So what it does here is mainly, it updates the balance. So it takes the from address, wait, what does it do here? Is this correct? It is correct. So so it just duplicates the value, it swaps them, puts them in the right place, it subtracts with a sub opcode to get the updated balance, and then it stores it, and then we emit the actual event with, again, a macro that helps us emit the event. It organizes stuff in memory, only does 16 bytes as discussed before, and then we finally have the actual ETH. So what this function does, actually, that's my bad. I didn't clarify the high level of what this function does. So this function withdraw from, what it does is that it uses an allowance to withdraw tokens from somebody else and then withdraw it as ETH. So you basically unwrap from somebody else. So I can say, okay, this would be useful, for example, in, I don't know, an application, not Uniswap, because Uniswap always uses ERC20s, but let's say like OpenSea, where the seller wants to receive ETH, but the buyer place their bid in wrapped ETH, right? Because the exchange needs to be able to asynchronously draw ETH from them. So then you could use withdraw from, because then what the exchange would do is it would use the allowance from the buyer to withdraw the ERC20 token METH from them, and then give the give the seller ETH at the end. So that's what the send ETH macro does at the very end, is it actually sends the ETH. And in the send ETH macro, I actually stop over here. So this makes sure that I have no reentrancy bug, because there's no state changes after. I can ensure that there's no state changes. So there might be a bug where the code doesn't work because I missed some state changes, but at least I don't have a reentrancy bug. Or I know I can't have a reentrancy bug because after the call, nothing else is going to happen. It always stops in here. So that's withdraw from. To summarize, we start with the function dispatcher, and then withdraw from, we check its selector, we check the message value. Then we calculate the allowance slot and see, withdraw from start. So we calculate the allowance slot, we get the allowance, we check if it's infinite, and then if it's not infinite, we actually update the allowance and check if it's sufficient. And then after that, we actually check if the balance is sufficient. And then after we've checked if the balance is sufficient, we actually update the balances, or in this case, the balance, because it's only the from address. Was the balance get updated, we emit the event, and we send the ETH. So that's one whole function, another whole function in Huff, and this is actually probably one of the most complicated functions that is in METH. All the other functions are a bit simpler in terms of like the branches and the tricks they use. Although I am planning to add the ERC 2612 permit functions back in, so that'll be it'll be smaller actually. It'll still be less complicated. Yeah, this is actually the most complicated function there is so far. Any questions up to this point, or what you thinking?
No, really interesting stuff, Philogy, and one question I have. This is obviously an insane amount of optimization and some really interesting tricks that you use to save gas. Aren't you like super afraid of a hard fork, soft fork that changes gas costs of any arbitrary opcode? I think that doesn't that scare you a little bit?
It does scare me a little bit, but I think at least from the EIPs that are on the horizon in terms of like they're already proposed, I've only seen proposals that actually reduce gas or introduce new opcodes that like change, that reduce gas. Like for example, one EIP I'm actually super excited about that changes the gas game completely is EIP 4200, because it changes how branching is done. So instead of these super expensive branch opcodes that I have to use here. So here you actually have a dynamic label which is pushed at runtime, and then you jump to it conditionally. You have new opcodes where the jump destination is fixed at runtime, and it only costs 2 gas. So here every conditional branch costs at the very least 13 up to 14 gas. With EIP 4200 as proposed now, every single conditional branch would only cost 2 gas. So the huge advantage already, one is I wouldn't have to do this weird optimization where I put all errors into one value and then check it once with one branch. I could actually check every individual value wherever it is, and that would actually save gas overall. And that would also allow me to have custom errors depending on where it actually fails. Because here, I can't have a custom error because I don't know why it failed, right? I have one global error value which accumulated all the different errors, and then I can't really revert with a different error depending on what it did. So actually I'm more excited than scared, but it could happen that they change the cost of opcodes. Like in the past, they massively revamped the cost of storage opcodes because they were underpriced, and they changed like how they were priced to make it more fair. So things like that could definitely change some of the trade-offs I'm making here. But most of the opcodes are like quite fundamental and quite basic, so I don't think their cost will change too dramatically. But yeah, you never know.
No, that makes sense. Okay, let's talk about compilers and stuff, because I think that's interesting. So there are still people left who write assembly, right? If you write a driver or you do some super low level stuff, system engineering thing. Obviously, the EVM space is a little bit different, I would say. Do you think we will ever get to the point where the Solidity compiler is just so good and does all these optimizations on its own, or do you believe that we'll always have a space for these super optimized contracts or languages?
I'm very optimistic that the compilers can be made better. I think there's a lot of room to make them better. I'm not exactly sure if Solidity specifically will do it, because Solidity's philosophy always seems to be maximizing safety, and therefore not adding too much complexity in terms of optimizers. And for example, I asked if it makes sense to contribute to the bytecode level optimizer, for example, in Solidity, and they said they don't want to see too many changes there because they've had some close calls with bugs in the past. And also with the recent Viper issue, I mean, it was fixed a long time ago, but I think people in general will just be more conservative in terms of fancy things that compilers can potentially do. So, but I do think there's a ton that can be done. Actually, I'm currently like learning Rust, and one of my small side projects that I'm using to learn Rust is writing a very simple decompiler for EVM bytecode, but eventually I want it to become like a general purpose optimizer. I'm not sure how far I'll get with that, and I'm not very far currently. But yeah, I think there's a lot of potential for compilers to do this, and specifically in the EVM smart contract space, I don't think this these super low level optimizations will be very useful or popular for long, because we're dealing with like mission critical software, right? We can't afford to have like a little bug or a little error. Like just writing the huff already, it has so many footguns and considerations, and just to get like all the performance, to squeeze all the performance gains out of it, it's just like so much effort, and just takes so much time to do it manually. So I think in practice, just like having better compilers will just mean that you'll be more optimized than huff contracts, because there's very few cases where you can't afford to spend weeks or months just building one contract. Because this contract, it seems like super big and complex here in huff, but actually super simple. Like my reference implementation in Solidity, even though I use inline assembly, is so much simpler. It's only 173 lines, and it implements all the same functions. And probably the gas use is, I mean, it's not quite the same. Obviously, it's a bit off, but even though I use even the same storage layout, right? I use like a little bit of inline assembly magic, so I can have the same storage layout where the address is directly the storage slot and things like that. But even then, the entire code is only 173 lines of relatively readable code, versus all this complexity just to save, versus this implementation, it probably only saves like, I don't know, less than 1%. So I think specifically for wrapped ether, the effort is worth it because of just how used it is. As I mentioned, 5 to 10% of all gas usage on Ethereum. but for most other projects, I don't think this level of effort is worth it. And that, better compilers are, better to invest your time in better compilers, because that's a one-time effort that'll benefit everyone, versus here, it's every application, it's a non-reusable effort essentially. So yeah.
No, that's a good point. How far is METH with auditing and stuff? Is there, because I can imagine there are not a lot of people who can audit this kind of stuff.
Yeah, so I've spoken to a few friends of mine in the EVM space, who are also like low-level optimizers and also auditors, who said they'd be interested in like reviewing and maybe even auditing the contract. And I've also spoken to people at Spearbit that they would also be able to audit it or like have the skills. So I think those are some people I can rely on. In terms of cost for auditing, I think it will be high, and I'll try to raise like some retroactive public goods funding and see what I can do in this regard. The code base is not yet at a point where I do want to start any audits, because just yesterday I discovered what I think is an optimization that I'm going to have to do some like slightly larger refactors for. And then also, as mentioned, I want to add the permit functions back in. Initially, I removed them for the sake of simplicity, and because I thought, okay, long term, we're going to have account abstraction. We're not going to need, it's not going to be very popular to use like specifically ECDCA-based permit schemes. But now I'm realizing that it looks like EOAs will stick around for a while more, and if the objective is to save gas, I might as well add them in. Like at this point, the contract is already so huge, like adding, I don't know, like 100, 150 lines for those functions will not change too much in the grand scheme of things. So yeah, that's why I'm thinking of adding them now. So yeah, it's not in the state yet where it will get audited, but I do want to get it formally verified. So I'm speaking with DXO from the Ethereum, not from the Ethereum fund. So they are working on HEVM, which is a symbolic execution and formal verification tool for smart contracts. And I'm working on using that for formally verifying METH to some degree, so that'll be useful as well. So yeah, to summarize, there is a smaller pool of people who can audit something like METH versus like a normal contract, but there are I think quite a few people who can do it that I'm confident could do a good job. And also, if I can get it formally verified, I'll also have personally much more, I'd sleep much better at night, knowing it's formally verified.
Yeah, for sure. No, listen, man, this was super cool. I learned a ton today. How for me, I wrote maybe 30 lines of code, looked at the documentation, but walking through an actual implementation of something was super interesting and super helpful. So thank you for that, and you did a really good job of explaining this. So yeah, thanks for taking the time, man.
Yeah, thanks for having me on, and I hope I didn't skim over too many things. If you or anybody else reading this has a question, feel free to tweet at me, or just even DM me. My DMs are open on Twitter, so if you have any questions, just let me know. I'm always glad to elaborate, or the comments are also a bit sparse, so I'd be down to also just document it better. So yeah, if you have any questions, please let me know anytime.
Awesome. Yeah, I'm gonna link Philogy's Twitter. Your Twitter is a must follow if you're into the stuff. Your blog as well. I'm gonna link that down below in the description. So yeah, Philogy, thanks for taking the time, and guys, see you on the next one. Bye bye. Take care. Bye bye.
Bye.